But let's continue on first with Faraday's law, which we introduced last time. Which says that there's an electric field, and specifically a non-Coulomb or Curly pattern of electric field associated with a changing magnetic field. So if you have a round-trip path integral of the electric field over a closed loop, and that is associated with a rate of change of magnetic flux through that loop. And we'll do more with this today in terms of calculations. We could also write this. We said that a round trip work per unit charge is what we call an EMF. So this thing really is an EMF, or not even round trip, but just a work per unit charge is not by a non-Coulomb force is an EMF. And we can also use the symbol phi sub m to indicate magnetic flux. So Faraday's law is that, and we were looking at the pattern and the direction specifically of the non-Coulomb electric field that's created or is present when you have a changing magnetic field. And we were talking about the steps, so direction of non-Coulomb electric field. Steps we were talking about in terms of getting the change in the magnetic field, and specifically getting the direction of the negative, or the delta B over delta T. So the first thing you have to do is draw your initial and final magnetic field, if there is a changing magnetic field at some point. Use that to determine graphically the direction of the change in magnetic field. Remember, when you're finding a difference in two vector quantities, you draw them tail to tail, and then the delta B points from the tip of the initial to the tip of the final. And then you have a right-hand rule, which says that your thumb, if I can spell, thumb, is in direction of negative dB dt, or if we're just making this approximation, delta B over delta T. And then that can give us fingers of your right hand curl in the direction of the non-Coulomb electric field. So last time we were just started to look at some cases where we had a changing magnetic field. And at first we were just looking at how to find delta B. Let's try to put this together and start with a question where we have the little demonstration that we showed last time. We had a bar magnet that was being moved through a coil, and we saw that there was a current. We say the current or the electric field is induced in the coil, meaning it's created but not by means of charges, but through this means of changing magnetic fields. So the first thing, if we want to find this induced current and induced electric field, we need to find this negative dB dt direction. Okay, so the first thing we want to do, we looked at that last time, so let's start here. So let's go through the steps. Okay, so really we're talking about the first four steps here. We want to find the direction of the magnetic field inside the coil, draw B initial. If you are moving, well, in this case, you're moving the bar magnet away from the coil. So here's the initial point of the bar magnet. Draw the initial magnetic field inside the coil. You move the bar magnet away, draw the final magnetic field, draw delta B, and then figure out the direction of negative dB dt. So let's try that. I see some people, but not many, actually drawing. I highly recommend you actually go through the steps by drawing something, drawing these vectors on a piece of paper, in your notes, somewhere, doesn't matter, because it's just too many steps to do in your head. So be careful about the direction of the axes here. Positive y is this. You have a coil. The way we've oriented this coil is in the xy plane, so it may be a little bit hard to see here because we're drawing it in perspective. Positive y is up. Positive x this way. Positive z is sort of coming out towards us, if you think of this as the towards us direction. So you're taking this bar magnet and moving it farther away. Okay, so just be careful of the orientation there. Okay, so we have a majority response. That's good. And the other popular answer is the opposite direction, so that's good too. The sign, we know at least it's not x, y, x or y. It's got to be something along the z-axis. The magnetic field, let's start with B. The magnetic field, okay, so we have this coil. And here's our z-axis. Positive z-axis is this way. So, and there's our bar magnet. So at the center of the coil, the magnetic field is pointing what direction? Negative z, right, into the board here. So negative z. So that's B initial. And then if I move it farther away, B final, how does that look? Smaller, same direction. Okay, so B final is that way. Delta B points, just delta B, the change in B points positive Z, right, from initial to final. So negative dB dt points in the negative Z direction. So number 6 is correct. Number 6 is correct. Okay, so let's draw that. And I'll draw in a different color here. We have negative delta B over delta T pointing in the negative Z direction. So then finally we can ask, at location A, which is at the very top of the coil here on the y-axis, we're doing the same thing. We're still moving this bar magnet away. What's the direction of the non-Coulomb electric field at that particular location? So it's got to be the positive x direction, right? Because the thumb is pointing into the board. We've got the direction of negative dB dt, or it's pointing along the negative z direction. So it's in like that, right? I curl my fingers around, and the point I'm interested in, the observation location I'm interested in, is the very top, right? So it's where your fingertips, the direction of your fingertips when I curl them to reach the very top of the loop. So at that point, I'm going to get an electric field pointing in that direction, right? And which is the positive x direction. So that would be the direction of E and C at that particular location. Okay. Questions here? Everybody try getting the hang of this? Okay, like I said earlier, you basically just have to go through the steps. There really isn't a shortcut. And because if you're thinking about just B, or just B initial, or just B final, that's not going to give you the correct direction necessarily. Okay, it's the change in B that matters, and so you need to figure out that change in B, and then use the negative of that to give you the directionality for the right-hand rule. Let's try one more similar sort of question. And now it's basically you take all the steps. Here is the bar magnet. We're now moving the bar magnet toward the coil in the negative Z direction. We're interested in an observation location B, which is on the positive x-axis. So the coil comes down and intersects the x-axis at this location. Go through the steps. Can you find the direction of the non-Coulomb electric field at location B? We get the positive y direction, right? Because we start by drawing the magnetic field, which is still going to be pointing into the coil here in the negative z direction. So that's B initial. And if we move it closer, then the magnetic field will increase. Okay, so B final is that way. So delta B has also got to be pointing into the board here. And then negative dB dt then is pointing out, right? So negative dB dt, or delta B over delta T, is pointing in the positive z direction. So you take your thumb of your right hand, curl it around, and then you have to curl it either all the way around or think about curling it, starting curling it here. And when you're at this part of the coil, your fingertips are pointing directly upward, right? So it's going to be pointing in the positive y direction. So we get an electric field. So yeah, 3. Electric field in the positive y direction. Okay? And then at the top, it would be pointing what direction? To the left, negative x. Okay? On the opposite side, it would be pointing down. On the bottom, positive x, and you get the idea. Okay? Curling around like that. Okay. So I think we're starting to get the hang of this. Let's try this one too. Here's a power supply. You have a power supply, a battery essentially connected to a resistor, and you have a wire that's wrapped around a piece of metal, for example, forming a solenoid. A solenoid is just a coil of wire, but it's a very long coil. The coil is longer than it is, much longer than it is wide. Okay, and when you turn the power supply on, you have a conventional current that is flowing in this direction. So it's coming. The conventional current is coming towards us at the top of that solenoid and going into the page at the bottom. And then you crank up the power supply. So this is a variable power supply. You increase the EMF, and therefore you slowly increase the current in the solenoid. So while the current is increasing, what's the direction of negative dB dt inside that solenoid? Okay, a little tougher this time because you have to remember what the direction of the magnetic field created by this current is going to be, right? And then you have to think about what's happening to that magnetic field. So it's essentially you have just think about a coil of wire or a loop of current. If I had a conventional current, let me just look edge on here. If I had a conventional current going in that direction, I were thinking about the magnetic field inside here. That makes a magnetic field pointing in what direction? Out, right? Out towards us, which you can get a number of different ways. You can think about either curling your fingers in the direction of the conventional current and the thumb points out, or you can think about your thumb in the direction of conventional current, your fingers would curl around, and the fingers would point out at the inside. Or most basically is just using the Biot-Savart law, where we say delta B is I mu naught over 4 pi, I delta L cross R hat over R squared. And so all the delta L's here, all the pieces of the current are going to contribute I delta L pointing that way, curl the fingers down toward the observation location, so R is pointing that way, R hat, and you get a magnetic field pointing out. Okay, so B is out. And let's draw it in blue. Okay? So that means in here, what's the direction of the magnetic field? It's, yeah, to the right. Okay, so you have a magnetic field pointing that direction inside that solenoid. What's happening to it? It's getting bigger. Okay, so B initial is this way, B final is this way, and longer. So the change in magnetic field, the delta B vector is to the right, but negative dB dt is going to be opposite direction, to the left. Okay. So the instantaneous rate of change of the magnetic field has a direction to the left. Okay, so 3 is correct. 3 is correct. So that means we're going to have an electric field, a non-Coulomb electric field, essentially, that's going to try to resist the applied electric field. Essentially, it's trying to resist the change in some sense. This thing is sometimes called an inductor. And we may have a chance to talk a little bit more about inductors next week. But it's essentially creating an EMF that's opposing the applied EMF. And they have various uses in electric applications, but we'll delay talking about that for a while.